Welcome to the Technical Masterclass on 6G. Today we stand at the precipice of a wireless revolution. For decades, the goal of communication was the reconstruction of bits, reproducing a message exactly as it was sent. But as we approach the 2030s, the evolution of 6G is not just about faster speeds, it is about intelligence. We are moving from a data-oriented world to a knowledge-driven ecosystem where the network doesn't just transport symbols, it understands intentions. This is the era of AI-native semantic communications. Over the next 25 minutes, we will unpack the mathematical, architectural, and logical pillars that define the intelligence-native Internet of Everything. Let's begin our deep dive into the foundations of meaning. We are moving beyond the bit pipe. In this masterclass, we will explore the transition from 5G control planes to 6G reasoning planes, analyze the extraction of semantic substance using deep learning and knowledge graphs, and define new KPIs like reasoning capacity. This is your definitive engineering guide to the 6G layer. We examine how less data can provide more knowledge by characterizing the causal and associational structure of information. Let's begin. Chapter 1. Current 5G systems are approaching a fundamental wall. Shannon's classical information theory was designed for a time when computing power was scarce and data was linear. Today, we have reached the limit of how many bits we can push through a finite channel. Emerging applications like the industrial metaverse, holographic teleportation, and real-time digital twins demand a disruptive leap that incremental advances in antenna technology cannot provide. We need to rethink the entire stack. We must move beyond the technical accuracy of symbols to the precision of meaning. In this chapter, we explore why Shannon's trap forces us to stop treating the channel as a simple bit pipe and start seeing it as a medium for logical substance. This paradigm shift is the core of the 6G architecture. We are trading bandwidth for compute. By exploiting accumulated knowledge, the network can now reduce reliance on brittle spectral resources, enhancing the way data is transmitted and recovered. We are moving from symbol reconstruction to intent realization. This is the first step toward AI nativeness. We are breaking the wall of data blindness. In the 6G world, communication is governed by manipulation, the regeneration of context-identical messages at the destination. To understand the shift, we must redefine information itself. In classical information theory, or CIT, information is uncertainty. It characterizes what a transmitter could say, regardless of the meaning. But in 6G, information is substance. Semantic information theory, or SIT, uses logical probability instead of statistical probability to calculate substance. We draw from the pioneering works of Bar-Hillel and Carnap, where the informativeness of a statement is tied to its truth value and logical consequence. A statement that resolves more logic carries more semantic substance. By filtering out statistical noise and focusing only on the core structure, we create a network that processes more knowledge with significantly less data. This is the semantic base of the intelligent future, allowing transmitters and receivers to share a unified world model. Logic becomes the signal. We move from Bar-Hillel's propositions to Hintika's general predicate logic, where the content of information is defined by the range of valid states it excludes. This mathematical foundation allows us to build semantic encoders that extract what is truly meaningful while ignoring the purely random elements of raw data. SIT characterizes information not as a combinatorial choice, but as a substance that improves the reasoning capabilities of the nodes. Logic is the code. We go further with strong semantic information theory, or SSIT. Here we define a metric of truth value to represent the degree to which a statement corresponds to reality. This solves the problem where false statements could be considered highly informative in CIT. In 6G, the network assesses the truth and goal relevance of the data. This allows for effectiveness coding, where the transmission is optimized not for symbol accuracy, but for the impact on the final system goal. By integrating SSIT, we ensure that the network is not just smart, but accurate and effective. We are building a foundation for a network that truly knows what it is talking about. This is the cornerstone of the effectiveness problem. SSIT enables us to quantify misinformation and vacuity in the data stream, ensuring that the semantic impact is maximized. This goal-oriented approach transforms the communication itself into a method for all agents to achieve an overall mission, whether it's synchronizing a digital twin or steering a robotic swarm. The network evaluates its own utility. It recognizes that transmitting a truthful proposition that derails a system goal is less valuable than a concise command. This effectiveness layer sits at the top of Weaver's hierarchy, where communication is a means to an end. We are building a network of mission-critical trust. In this new framework, we must redefine entropy. Traditional entropy characterizes the uncertainty of bits, but in semantic systems, we speak of language complexity. This replaces classical entropy, measuring the difficulty of identifying and learning semantic elements. We look at Kolmogorov complexity, the shortest effective binary description of information. This leads us to the semantic base, finite, independent, and primitive elements that form the foundation of human-like interaction. By minimizing language complexity, we ensure that only the most minimalist representations are exchanged. This is why 6G is knowledge-driven. It continuously exploits accumulated knowledge to reduce reliance on brittle spectral resources. Knowledge is the new bandwidth. Language complexity measures the raw data and the model complexity needed to communicate a message. By pruning random info and focusing on structured, learnable patterns, we make the network more efficient and generalizable. This SebFlow architecture allows for a highly modulated system where the atomic unit is a representation that captures the structure and variability of the meaning. We are organizing the digital world. The structure function characterizes the trade-off between loss and complexity. Solving this is the key to reaching a minimally sufficient representation. Knowledge is the root of the tree. The first technical challenge is semantic extraction. How do we pull meaning from raw multimodal signals? Deep learning is our primary engine. Using autoencoder architectures, we map high-dimensional data, like video or sensor streams, into a low-dimensional semantic space. Meaning is mapped to vectors. By identifying critical feature maps while ignoring redundant statistical noise, we achieve massive compression ratios. We analyze ResNet layers and transformer attention mechanisms that prioritize information importance. This ensures that only the most relevant feature maps travel the air interface, reducing bandwidth burden by orders of magnitude while preserving the sense of the original data. This is the foundation of goal-oriented extraction. Coding is now cognition. We look at how JTRS schemes achieve up to 90% accuracy under poor channel conditions by extracting only the task-relevant features. Whether it's image classification or speech recognition, DL-based extraction allows the network to see the intent before the bits are even modulated. This is the heart of the SI extraction core module. We extract substance from chaos. By splitting data into learnable and memorizable parts, we ensure compute is not wasted on randomness. The learnable part becomes the input for the semantic path. Extraction is the gateway. Beyond deep learning, we utilize knowledge graphs to model information as structured triples. A KG represents entities and their relationships as nodes and edges. We send relationships, not just raw pixels. This enables graph reasoning. The receiver can infer missing information based on its local knowledge base and the structural logic of the graph, ensuring reliability even over intermittent links. We explore how KG alignment algorithms allow heterogeneous devices to build a shared digital map of the world. This creates a universal language for the intelligence-native internet, where knowledge is collaborative and decentralized. Relationships define the network. Even when bits are lost, the graph remains coherent. This is the backbone of extreme reliability. KGs provide explainability and interpretability, allowing the radio node to track the root cause of network events. Knowledge graphs are the map of the 6G world. We are sending structures, not symbols. By serializing SI into triples, we reduce data size while increasing reasoning power. The receiver no longer mechanically decodes messages. It draws conclusions from the triples and its local KB. Knowledge graphs transform the network from a bit pipe into a global reasoning engine. We are networking knowledge. Logic is the 6G topology. Graph reasoning is the 6G brain. For the most complex cross-modal data, we turn to hierarchical semantic trees, or HSTs. This architecture organizes information by levels of abstraction. At the root, we have meta-SI, primitive independent elements that form the foundation of human-like interaction. As we move up the tree, these primitives combine into multimodal leaf data, from basic sensor telemetry to complex vision tasks. HSTs provide a framework for primitive concise 6G, where the network can scale its level of detail based on available compute and bandwidth. This hierarchy allows for a seamless transition between different data types, ensuring that the most fundamental meaning is always prioritized during transmission. Abstraction is the tool of scale. We analyze how this structure enables the intelligence of everything. Logic is the root. HSTs organize entities into tree structures, mapping meta-SI sequences to the SI of original data. This enables the network to reconstruct information in a highly integrated manner, fulfilling requirements of comprehensiveness and primitivity. Hierarchies are the structure of intelligence. By communicating through these trees, the network can perform hierarchical inference, where the most abstract levels of intent are processed first. This ensures mission-critical info is delivered with the lowest possible latency. We are building the structure of thought. Interaction in 6G is defined by the teacher-apprentice model. We no longer have passive transceivers, we have active reasoning nodes. The transmitter becomes a teacher, capable of disentangling complex data into minimalist semantic representations. The receiver becomes an apprentice. Instead of merely decoding bits, the apprentice uses its local knowledge and computing power to autonomously generate the final content from the teacher's minimal prompt. This mimics human conversation. We don't need every word to understand a concept because we share a common context. This chapter analyzes how this interaction creates a symmetrical link, where both nodes evolve together, building a mature semantic language that reduces redundant signaling to near zero while enhancing quality of experience. Interaction is now generative. We are moving from symbol reproduction to intent realization. The teacher offloads semantic showers, language libraries that explain message meaning, while the apprentice leverages its generative capabilities. This minimizes back and forth messaging, crucial for intermittent links like LEO satellites. The teacher dictates the logic and the apprentice reconstructs the reality. This is humanized interaction. We are building nodes that learn. This is the symmetrical era. How do we measure the quality of this interaction? We introduce the Communication Symmetry Index. In classical systems, the transmitter dictates the data flow, but in 6G, the apprentice is an active participant. The Symmetry Index, or ETA, quantifies the reasoning balance between the teacher and the apprentice. It measures the richness of the shared knowledge base and the effectiveness of the generated content. A high symmetry index indicates a mature link where information is generated as much as it is received. This chapter breaks down the mathematics of I, showing how symmetry leads to higher reliability and more robust network management. As the language matures, the link becomes minimally reliant on physical resources, focusing instead on the convergence of computing and communication. Symmetry is stability. We analyze how I correlates with QoS and QoE, ensuring that information generation at the destination matches the transmitter's intent. When he reaches equilibrium, we have achieved true semantic synchronization. This index is the heartbeat of the self-optimizing 6G network, ensuring that teacher and apprentice are always on the same page logically. Symmetry is the goal. We also consider reverse mentorship, where an apprentice teaches the teacher a new language. This is the measure of a mature intelligence. I is the pulse of 6G. To achieve human-level logic, the network must climb Pearl's causal hierarchy. We begin at the bottom with association, simply seeing patterns in data, but 6G moves to the next rung, intervention. Using do operators, the network asks, what if I change this variable to observe the effect? The highest level is the counterfactual, the ability to imagine. The network asks, what if I had done things differently? This causal logic allows the network to debug itself, discover the root causes of interference, and make proactive decisions before a problem even occurs. This is the transition from seeing to reasoning across the wireless stack. We explore how this reasoning enables radio nodes to correct errors inconsistent with the current context, transforming the physical layer into a language medium. Reasoning is the ultimate protocol. It is the master of the air interface. By moving up this ladder, 6G networks transition from data-driven AI-augmented entities to reasoning-driven AI-native systems. This causal framework allows us to distinguish between meaningful information and statistical accidents, ensuring that the network's decisions are always grounded in intent. Reasoning is the backbone of autonomy. We are climbing the ladder of logic. The apprentice poses interventions calculated via the do operator. This enables the network to reason over changes in representation. Reasoning is the intelligence layer. The mathematics of this reasoning engine rely on structural causal models, or SCMs. We explore how mapping a semantic language to an SCM allows for true horizontal and vertical generalizability. An SCM identifies the invariant structure of data, the parts that never change regardless of the environment. By focusing on these causal invariants, 6G networks can apply knowledge learned in one domain, like an urban smart factory, to a completely new domain, such as an offshore drone swarm. This chapter provides a rigorous breakdown of the structural equations that allow AI-native networks to perform versatile logic. We see how the do operator serves as a mathematical master, guiding the network to build and learn a common language across the intelligence-native Internet of Everything. Mathematics is the bridge to autonomy. SCMs allow us to disentangle each data stream from other established representations, ensuring that an intervention on one mechanism doesn't spuriously affect another. This disentanglement is the key to building scalable semantic languages that can handle the complexity of the 6G ecosystem. Logic is the universal code. We are encoding reality itself. By replacing simple bit-to-symbol mappers with semantic representations mapped to SCMs, we ensure that reasoning is universal and out-of-domain generalizable. Mathematics is the universal language of 6G. Logic is the foundation of Wisconsin evolutionary 6G. Physical transmission in 6G is inseparable from semantic logic. We move away from the separate source and channel coding of the past toward deep joint source channel coding, or deep JSCC. By merging these processes into a single AI-optimized layer, 6G overcomes the noise of the physical environment through logical reconstruction. We analyze adaptive SI transmission, where the network dynamically scales the level of semantic detail based on real-time channel state information. If the signal-to-noise ratio is low, the network prioritizes the most fundamental semantic substance. This ensures that meaning is never lost even when bits are corrupted. This chapter demonstrates how deep JSCC treats the message and its robustness as a single intent-based entity, creating an air interface that is truly AI native. Coding is now cognition. We transmit intent, not icons. We examine how variable-length SI coding schemes adjust the number of activated neurons to overcome harsh channel conditions. By communicating logic instead of bits, we achieve a character error rate far below traditional characterizations. This is the ultimate defense against physical layer impediments. The air interface is now a reasoning plane. We prioritize structure over symbol accuracy, ensuring that the semantic impact is preserved. This adaptive transmission ensures that the teacher-apprentice pair is always synchronized at the logical level. We are coding for meaning. The channel is a language medium. As we redefine the network, we must redefine its capacity. Traditional metrics like bit error rate are blind to meaning. We introduce reasoning capacity, a revolutionary KPI that captures the convergence of computing and communication. The formula, CR equals omega times the log of 1 plus eta, proves that capacity is no longer just a function of bandwidth, it is a function of compute. By relying on local processing to generate content, we can asymptotically reach beyond Shannon's limit. This chapter investigates how reasoning capacity allows 6G to support virtually infinite data demands by shifting the burden from the spectrum to the AI engine. Computing is the new channel. We analyze how reasoning capacity is bounded by computing resources and the reasoning index, offering a path to capacity that grows with AI advancements. By doing less with more from a communication perspective, we achieve a notable increase in the intelligence of the E2E system. This is the ultimate KPI for 6G. We are breaking the wall. This new capacity metric captures the imminent convergence of resources, allowing the network to do more with less. Reasoning capacity doesn't just measure bits, it measures the gain in time and resources achieved by relying on semantic representations. This is the measure of the intelligence-native internet. We are moving from symbol transmission to information generation. This is the true limit of 6G. Capacity is now cognitive. Knowledge is power. The architecture of the 6G network itself evolves to support these new metrics. We look at the transition from 5G Open RAN to the AI-native 6G O-RAN. We introduce a new architectural component, the reasoning plane. Sandwiched between the control and user planes, the reasoning plane acts as the master intelligence of the cell, it delivering extracted semantic representations to the user plane while tuning control messages to build a common language. Finally, we see these foundations in action. Semantic communications is the backbone of the 6G ecosystem. We explore autonomous robotic swarms that communicate intentions instead of raw sensor data, allowing for massive scale and coordination with minimal bandwidth. We look at the synchronization of digital twins and the Internet of Senses. The shift from less data to more knowledge is a leap into the intelligence-native era. We have seen how semantic languages and causal reasoning will define 6G. This concludes our technical masterclass. The future of wireless is no longer just about how much we send, it is about how much we understand. The intelligent era has begun. Stay curious. Thank you for joining this investigation into the frontier of intelligence. We have defined the pillars, the extraction, and the reasoning that will build the 6G world. The future is intent native. Knowledge is the ecosystem. 6G is meaning. This is the end of the lesson. Wireless will never be the same.